Okay, welcome back, everybody. Once you've marked yourself off on the attendance sheet, may I please invite you to stow your electronic devices, and we will get back to evolutionary robotics. A couple logistical things this morning before we get back to the meat of the lectures. I'm a COVID close contact as of yesterday, so I'm masked up. Let's see. How did everything go with submissions last night? All good? Okay. Hardest thing in this class is getting PyBullet installed for some of you. Some of you it's trivial. If you're still having PyBullet installation issues, as I mentioned, don't get behind in the assignments. Come and see Krishna, the TA, or myself as soon as possible if you have any lingering installation issues. You've had a week to get used to this class. Hopefully you figured out how to submit things. You write things up on your own laptop, record a video, send it to the moon, to Reddit, to YouTube, to here, there, finally back to Blackboard. We're all good. For our purposes, for grading, for the TA and for myself, when we go to grade your submission in Blackboard, we should find a set of links. It doesn't matter to us whether they're Reddit links, YouTube links. All we expect is that when we click on it, you're showing us what you managed to accomplish. As long as we can do that, we're all good. Good? Any questions about the mechanics of the assignments? Submission? All good? Okay. So let's talk a little bit just about the assignments themselves. We're going to start to speed up a little bit now, at least for the undergraduates. In these first few assignments, you're obviously building your virtual robot in the virtual environment. As we mentioned last week, there's 4 sort of building blocks for any evolutionary robotics experiment: the environment in which the robot lives, the robot itself, the neural network that transforms the robot's perceptions into actions, and then some sort of AI, which in our case is going to be an evolutionary algorithm, that modifies the neural network controller of the robot, and later in the course, also the body of the robot to get the robot to do whatever you want it to do. Those are the 4 main building blocks. If we drill down into a robot itself, the robot is made up of 6 building blocks or types of building blocks. Links, which hopefully now you're already familiar with, which are the physical objects that make up the robot, right? Upper arm, lower arm, hand, finger, phalange, and so on. The bits, the parts that make up the robot. For the undergraduates in assignment 2, you're going to tackle joints, which are the things that connect links together, which we'll talk about in a moment. There's a couple things to get straight when you're working with joints in the particular physics engine that we're working on in this class, which is PyBullet. Once you have the physical structure of your robot set, you have basically a statue or a rag doll. It's not a robot yet. It has no way to sense and act in its environment. So for the graduate students in assignment 3, which you will be working on this week, you're going to be adding sensors to the robot so it has some way to perceive its environment. You're going to be adding in assignment 4 for the graduate students this week, you're then going to be adding motors to your robot. Motors are the robot's equivalent of muscle, the way that it's able to apply force to the links that make up the body. I'm sorry, I misspoke. The motors are connected to the joints. The motors are going to pull and push on the joints, and the joints connect links together. So we go from motors to joints to links to start to get robot action. Yeah? Sound good? Okay. I mentioned last time the sense, think, act loop in robotics and in us. So there's 2 more pieces that we're missing to complete this picture. What are those 2 additional pieces?
The brain.
The brain itself, right? So we've got sense and act, but we don't have think yet. So in assignments 5 and 6, which the graduate students will get to next week, you're going to be adding neurons that make up the robot's brain or the robot's neural controller. And then finally, synapses, which in your robot's case are little wires that attach the sensors to the neurons to each other, and then the neurons to the motors. These two together will complete the sense, think, act cycle. So this is basically what you're accomplishing in the first 6 assignments. We'll talk about 7, 8, 9, and 10 later. So far, so good? Okay, so let's take a moment and talk about joints. For our purposes, you're going to be implementing joints that are very similar to your elbow joint and your knee joint, which connect objects together and constrain their motion. My upper arm cannot move towards the door while my upper arm stays here. There are particular ways that these two parts can no longer move relative to one another thanks to my elbow joint, right? So the basic definition of what a joint is in PyBullet and in biomechanics in us is that they constrain the relative motion of the two parts, the two links that they attach together. So far, so good? There's lots and lots of different kinds of joints you can create in PyBullet that constrain the relative motion of connected joints. For example, our shoulder joint acts very differently from our knee and our elbow joint. It constrains less the relative motion of my upper arm relative to my torso. You can create the equivalent of a shoulder joint in PyBullet. There are also pistons which allow objects to change their horizontal position relative to one another. You can have two objects that extend and contract back. We saw an example of pistons making up a robot from last week. Where did we see pistons already?
What was the one you made?
The nanoped, right? These two Stewart platforms, which are basically two sets of 6 pistons, right? Pull and push. Yeah? Okay. Lots of different kinds of joints in PyBullet. For the first 10 weeks, for the undergraduates, we're going to restrict ourselves to rotational joints like our elbows and knees that allow the connected objects to rotate relative to one another, but not move relative to one another. So far, so good? Okay. All right, so we started with links because it's obviously the most obvious thing that you can see and manipulate in PyBullet. It's relatively easy to debug your code when you're creating links in a physics engine because obviously you can see the links. If you get the size wrong or the position wrong, the moment you open the simulation window, you can see it. All the remaining 5 types of parts that you're going to be implementing in these assignments, you cannot see. They're invisible in the physics engine. So it's going to take a little bit more work and a little bit more vigilance on your part to make sure that they work correctly, which is why you're sending us videos. We will not be able to see your joints and sensors and motors either, but we know what we expect to see in that video, and we'll talk a little bit about what you should expect to see when joints are working well and when joints are not working well in a physics engine this morning. Okay, so let's talk about joints. You will find in Learning Module E, the joints module here, you'll find a link somewhere down here. Down in step 29 here, you'll see a link to a slide deck. Make good use of this slide deck to build up an intuition for how joints work. Once you absorb that, you should be good. Okay, so I want to just walk through the slide deck a little bit this morning to make sure we're all on the same page. Okay. All right, you've just finished the link assignment, which is pretty straightforward. In that assignment, you define the position of a link, which is where in the world is the center of that link, of that object. Yeah? I'm going to build up a cartoon example here where we're placing a cube at x equals 0, y equals 0, z equals 0.5 units off the ground. I'm not very good at drawing in 3D, so we're only going to create this robot in y and z coordinates. Hopefully you figured out the coordinate system now in PyBullet. X is as you would expect, horizontally. Y is into and out of the screen, and Z is up and down. Yeah? Okay. So I'm going to plot some links and joints here. We're going to place them at various positions where they have different Y and Z, but we're just going to leave X as is. Yeah? Okay. When we create a link, not surprisingly, when we create a joint, like for a link, we need to define the position of that joint. It's easy to get that position wrong, and because the joint itself is invisible, it's hard to know whether you got it in the right place or not. Yeah? Okay. To start with, we're going to define the position of joints in absolute coordinates, like we did for links. What do I mean by absolute coordinates? I mean, these are coordinates that are relative to the world. You can think about this like GPS or latitude and longitude. These numbers refer to positions in the virtual world. Kind of straightforward, yeah? Okay. Let's imagine in this cartoon example, we create a second link. It has the very creative name of 1. We're going to name our joint here 0_1 to remind us that this particular joint is connecting together links 0 and 1. Yeah? The position of the joint here you can see is at x equals 0, y equals 0, z equals 1. And the center of this new link that we're creating is at position 0, 0, 1.5. Pretty straightforward. Questions?
Do links have collision with each other?
Do links have collision with each other? I do not think they do by default, but you can turn it on. Yeah? Good question. We'll come to collisions a little bit later in the course. Okay. We could continue this and make, for example, a robot made up of these seven links. For all of the things you're going to be doing, if you have n links, you have n parts that make up your robot, you're going to have n-1 joints, right? They connect pairs of objects together. And not surprisingly, we're always putting these joints at the place where these two links come into contact with one another, not unlike my elbow joint, which exists at the intersection between my lower arm and my upper arm. Yeah? Nothing too surprising here. This is not how PyBullet defines coordinates. This is the intuitive way you would imagine doing it. This is not how it's done. I mentioned this last week. This is one of the drawbacks of PyBullet. It mixes absolute and relative coordinates. So let's redo this example, but we're going to redefine it using the format that works for PyBullet. We're going to start, as usual, with our link down here. We're defining it in absolute coordinates. The center of this object is at 0, 0.5. We create our first joint here. It also has an absolute coordinate. It is sitting at 0, 0, z equals 1. So far, so good. The moment we come to add our second link, we are now going to switch from absolute coordinates to relative coordinates. And I'll explain why PyBullet does this in a moment, but let's just make sure we understand this mixture. Why are we switching from absolute to relative? For every link and joint that you add, if it has an upstream joint, if it has an upstream joint, you're going to use relative coordinates. What do I mean by an upstream joint? Let's have a look at link number 1 here. We are going to attempt to connect link 1 to 0 with a joint that is upstream. We added this object, or this link. We then added this link. We're now adding a joint that connects this new link to a link that we've already defined using this joint. So this particular joint is upstream from this, this link is upstream, this joint is upstream from this link, this new link that we're adding. If we look at this particular link here, there is nothing upstream. Yeah? We're building sort of up and to the right and down. We're going downstream as we add stuff. And as we're adding stuff, if we look back and there is an upstream joint, we're going to use relative coordinates. The coordinates are going to be relative to that upstream joint. So far, so good? Okay. So in this cartoon example here, This particular link has an upstream joint. So we are defining the center of link 1, the link called 1, to be z equals 0.5 units above the upstream joint. Now we've switched to relative coordinates. So these three numbers are no longer GPS. They're not defining a position in the world. They're defining a position inside the robot, relative to stuff inside the robot. Question?
Would that mean that, like, whatever robot we create will only have one absolute place link, and everything else is going to be relative?
Absolutely. So the first link is always going to be defined with absolute coordinates because the first link has no upstream joint. Yeah, it's always going to be absolute. When we start adding joints, they can be absolute or relative coordinates. We'll get to that in a moment. We're just focusing on links for a moment. The second and subsequent links, anything beyond the first one, they're always going to have relative coordinates. Question?
Is that even if they're connecting to the initial link again?
Exactly. So let's imagine we put another block here, for example. We'll call this link 7. And we want to connect link 7 down here to link 0. We're going to connect it with a joint here. We would create a joint called 0 subscript 7. Link 7 would have an upstream joint. The upstream joint would be joint 0 sub 7. So we would define the position of link 7 to be relative to its upstream joint, which would be sitting right here. So far, so good? A little confusing.
If link 7 were also connected to link 6,
Aha.
what would be the upstream joint?
Great question. Okay, so let's continue with this. So you'll notice as we're connecting these objects together with joints, we have a line here of connected things. The question here is, what if we put link 7 down here, connected link 7 to link 0, and then we connected link 7 to link 6? You would basically create a cycle, right? You'd have a circle of things that are connected together. That's a big no-no in PyBullet. You cannot do that. Anybody worked with physics engines before? Anybody know why that's not allowed? What you're looking at here, and we probably won't go into this too much in this class, is you're looking at what's known as a kinematic chain. You have a chain of objects connected in a series. A kinematic chain. Kinematic meaning motion. So you have a chain of objects where the motion of one is affecting the motion of the other. We have forces that are flowing back and forth. These objects are pushing and pulling and rotating one another. If we create a kinematic cycle, that makes huge headaches for the physics engine. Forces start to propagate around and then they come back again. It's very difficult for a physics engine to basically conserve energy. You remember here in the real world, energy is conserved. It's a very difficult bookkeeping task for the physics engine. It gets much, much harder to do when you have kinematic cycles. So we're only creating kinematic chains. Question?
Does that make things like I'm imagining like a tread or something like that, like a caterpillar?
Yeah,
thing.
right. So if you wanted to make a tank tread,
Yeah.
it's possible in PyBullet. You do it without a kinematic cycle. And if anybody wants to tackle that in their final project, we can talk about how to do that. Yeah. Okay. Okay. Any other questions before we get back to coordinates? Okay. So let's continue our cartoon example here. We've created link 0. We've created joint 0, 1. We've created link 1. And then joint 0, 1 is going to connect link 1 to link 0. We're then going to add a second joint, 1, 2, in preparation to connect a new object, a new link 2 to 1. Here's its position. The position of this second joint, this new joint that we're adding, also has a relative position because it also has an upstream joint, which is represented by this black curved arrow here, right? If we walk backwards along this kinematic chain from 2 to 1, 2 to 1 to 0, 1, we can see that 0, 1 is upstream of 1, 2. Everybody see that? So we define the position of this new joint relative to its upstream joint, and we indicate that the position of joint 1, 2 should be 1 unit above joint 0, 1. So far, so good? Okay, so this cartoon example here is meant to illustrate what's written in the assignment, the golden rule here for joints, which is that on step 32 here, only the first link that you create, the first physical object in the robot, has an absolute position. Every other link has a position that's defined relative to its upstream joint. Yeah, we covered that already. Step 36, when we think about adding joints, joints with no upstream joint have absolute coordinates. Every other joint has a position that's relative to its upstream joint. It's a lot to digest. Have a look at the cartoon in the slide deck. You'll get lots of practice in assignment 2 doing this. You'll notice that the wording is a little bit different in step 32 and step 36. There is no root joint. And we actually already described the reason for that. If we create link 7 here and connect link 7 to link 0, so we create a joint here called 0, 7, that joint has no upstream joint, but it's the second joint we're adding, right? We could add yet another object over here and add another link over here, connect that link to this link with a joint sitting right here. That joint also would have no upstream joint, so it would be defined with absolute coordinates, GPS coordinates, numbers that indicate where it exists in the virtual world. Okay. You can work your way through this slide deck, and I would suggest, I've left off the numbers here, I've just left them as question marks. Make a copy of this slide deck and replace the question marks with the actual numbers. I would suggest if you're still feeling uncomfortable with absolute and relative coordinates in PyBullet, I would suggest actually implementing this in assignment 2. You can play around with it in GitHub, roll back to the branch with your little robot that you're making, and on you go. Yeah? For the undergraduates, you're only working on joints in assignment 2. Get started early. Make sure you absorb this intuition of mixtures and absolute and relative coordinates. It'll serve you well later in the assignments when we start making bigger and more complex robots with many, many more links and joints. Yep. Any questions? Piper.
Is it just arbitrary that it's all relative to the upstream joint rather than the upstream link? Like, why aren't they all relative to the first link?
Yeah, good question. So it's related to the question I'm going to ask now, which is, why the heck did the PyBullet coders inflict this pain on you? Why not just make everything absolute?
If you want to reuse stuff, then it would not make sense to have things relative to the world.
Absolutely. So one of the things you can do in the final project is you can make a swarm of robots. You could make multiple copies of this robot, where all you need to do when you create the copy is redefine the 2 absolute coordinates here. You need to tell it where the start of the second robot in the swarm is, its first link, and its joints, and then all these other numbers stay the same because they're relative to numbers inside this second robot that's being constructed inside the swarm. Now that I think about your question, Piper, you're right. You could still benefit from that where it doesn't have to be relative to joints. It could be links. I don't know. For those of you that don't make a swarm, that only make one robot, this is only going to be pain. There's no benefit. Sorry. If you make a swarm, you will benefit from digesting this intuition. Yeah? Okay. Okay. I think sensors and motors, grad students, you can start in on that. For the undergrads, we'll talk about sensors at the beginning of class next Tuesday. Okay, I think that's all I had to say about assignment 2. So back to our theme on introduction to evolutionary robotics. We talked last week about motivation. Why build robots? Why evolve robots? We started in on our very short history of AI. We got to the 80s. We'll jump back to the 80s in a moment, finish that off, and then we'll start in on our third lecture slide deck on embodied cognition. Okay, so we started last time in the 1600s. We talked about Cartesian dualism, jumped 300 years forward to the 1930s, the beginnings of the formalism of computation and computers. We jumped another 20 years ahead to the 1950s, the very first use of the word AI. We talked about, we kind of went back to why you might want to build robots. They hopefully will tell us something about biological evolution or biological intelligence or intelligence in general. We visited the 1960s, the very first chatbot, Eliza. We talked about the Turing test, and we ended in the 1980s with the Chinese room. This was John Searle's response or rebuttal to the Turing test. For Searle, the Turing test is flawed because there are things like the hypothetical Chinese room that can pass the Turing test. They could fool humans into not being sure whether they're talking to a human or a computer. This thing passes the Turing test, but it shouldn't pass the Turing test, according to Searle, because the Chinese room does not understand Chinese. You all good with that? We are different. Whatever is going on inside your head, and the Chinese room is meant to be a metaphor for your skull, whatever is going on under the hood, we are different. We really understand. If you learn Chinese and you speak to a native speaker of Chinese and they feel that you're very fluent, you understand Chinese differently from the Chinese room. Whatever it is you're doing, it's different. Everybody okay with that? Seems obvious. What's different? Now, there is a person inside the Chinese room, which can be a little bit confusing. But remember, this person is basically an automaton. They do not understand Chinese. They are just taking these squiggles. They go to this book. This book is written in a language that the person understands, which in this case is English. And the English instructions say, if you see this set of squiggly marks, write this other set of squiggly marks on the piece of paper and repeat, right? This thing is basically responding to a huge set of if-then-else rules. Yeah? So what's different?
You're actually like using like the semantics of what's being passed in.
Maybe. Define semantics.
Like the meaning, like the actual like meaning of the words, like you're interpreting like
The actual meaning of the words. Define actual meaning. I don't mean to pick on you. This is what is problematic about the Chinese room, is when you try and define what's different between us and the Chinese room, the further down you go, the harder it gets. Question?
Yeah, so
Yep.
The Turing test is so like if a human thinks they're talking to a real person, but it's really a computer or something.
Then the computers pass the Turing test. Yeah? Turing said there is no good definition of intelligence. We just can't seem to define it formally. So let's come up with an empirical way, an experimental way to determine whether something is intelligent. The definition of intelligence is it fools other humans into thinking it's intelligent.
Okay.
There are a whole bunch of intelligent things sitting in this room. I have not seen inside any of your skulls. As far as I can tell, you're all pretty intelligent. You're all passing the Turing test. That's it. That's the definition of intelligence. That's, according to Turing, that's the best that we have. For Searle, he said, it's not good enough. The bar is too low. There are things that can pass the Turing test that are not intelligent in the way that we are. For many people, this was problematic because it actually proves the opposite. There is nothing going on inside your head other than a whole bunch of electrical signals, which are just a biological equivalent of looking things up in an if-then-else statement. Or maybe today, it's just a deep network. There's a whole bunch of neurons and synapses. No neuron in your head understands English or whatever your native language is. There's no synapse that understands English. Does a collection of neurons understand? It's not so clear. Yeah? So for many people, Searle's thought experiment here backfired. It actually proved that this is understanding. You can have inanimate things, things that are made up of non-thinking things, and you put those non-thinking things together, and you have something that acts as if it's intelligence. That is intelligence. That is understanding. We feel, for very good reason, we're different, we're better. There's some additional magic going on there. We're not just executing a whole bunch of if-then-else statements or a whole bunch of complex electrical signals. Whether you agree with that or not, this has been around for a very long time. There's a fascinating debate around the Chinese room that is still going strong 44 years in. Yep.
Would we be creating our own if-then-else statements through learning experiences and parenting as opposed to a computer given it?
Possibly. So maybe this Chinese room, we attach some legs and arms to it and eyes, and it starts moving around. It bumps into things in the world, and some of those experiences with the world cause parts of this book to be rewritten without any understanding. You could define learning and human development in that way. Where is the magic sauce? There are arguments you can make that incorporate embodiment, the ability to move in the world and learn from the world. That still gives you inside this thing a collection of unthinking things, which eventually ends up passing the Turing test. It's difficult to pin down, for many of us, it's difficult to pin down exactly what differentiates us from the Chinese room. So many of us come to the conclusion, that's it. We are Chinese rooms. I am not here to try and convince you that you are a Chinese room, just to show you an example of some of the interesting debates in AI. As I promised you at the beginning of this course, robotics and AI is a bit of a challenge to us in our complacency. I think, I have emotions, I have free will, I plan. It feels obvious that I have those things, but that's just intuition. It's just felt experience. Maybe we shouldn't be as sure as we think we are about these aspects of what's going on in here. Yeah? Question?
You said many. You said many of us.
Yep.
So is there some people that have figured out this sauce, or?
Well, there's two camps. There's some camps that say there just is some sauce. Here's one of those members right here. There's this other thing called soul, or spirit, or mind, whatever, or consciousness, sentience, whatever you want to call it. It's in there. We've never actually measured it. There may be no scientific way to measure it, which is why I'm sort of referring to it not very charitably as magic sauce, right? There may be stuff in there that does differentiate us from the Chinese room. We've been looking for it for a long time. We haven't quite found it yet. So maybe it's there, maybe it's not. If you can figure out a scientific experiment to detect the presence of consciousness or sentience or free will, I would love to hear from you. As I mentioned, there's several Nobel Prizes waiting to be won in this area. That's probably one of them. Okay. Meanwhile, in the 1980s, elsewhere, Valentino Breitenberg wrote this book called Vehicles. Valentino Breitenberg was a neurophysiologist, meaning he studied the architecture of brains. Not in humans. He worked primarily in fruit flies. Again, if you've ever lived in student housing, you have first-person experience with fruit flies. They love rotting food. If there was a rotting apple in the back corner of this room and I had a little vial of fruit flies and let them go, they would move around in a cloud for a while, and after a few seconds or a few minutes, they'd start to head over there, and by the end of class, you went and looked, they'd all be on the rotten fruit. How do fruit flies find rotting fruit? You know how big a fruit fly is, about the size of a head of a pin. Imagine the size of the brain of a fruit fly. Super, super, super tiny. In the 60s and 70s, neurophysiologists were publishing papers that fruit flies were probably performing differential calculus and taking the integral of the curl of the flow of air currents and the smell of fruit and using that to differentiate their vector of flight to head towards the fruit. Breitenberg, who'd spent a lot of time actually dissecting the brains of fruit flies, thought this seems a little strange. That's a lot of cognitive machinery to impute or believe exists inside this little machinery. So Breitenberg started thinking to himself, if you had an object, it could be an organism, it could be a robot, it could be a vehicle. He eventually wrote this book, Vehicles. For Breitenberg, vehicle was meant to be, it didn't mean a car or a drone. Vehicle was meant to be an umbrella term for anything that senses, thinks, and acts. So organisms, us, robots, drones, autonomous cars, you name it. What's the simplest brain for a vehicle you could imagine that would allow it to fly through three-dimensional space and eventually find something of interest like rotting fruit? Yeah? The thing that surprised Breitenberg and surprised many people after him is the answer is pretty simple. You can make a brain very, very simple that leads to what looks like complex behavior, flying through three-dimensional space and finding the rotting fruit. He eventually wrote this up in this book. This book is broken up into a series of chapters. And if you read this book, it actually reads like a fairy tale. Once upon a time, there was a vehicle named Vehicle 1, and it lived in this kind of world, and it did this sort of thing. Next chapter, Vehicle 2. Once upon a time, there was a vehicle called Vehicle 2. It was slightly more complicated. It did this and did this and did this. By chapters 11, 12, 13, and 14, he starts to get into choices, planning, free will, emotions, sentience, you name it. If there's anything you read in this class, I highly recommend Vehicles. It's a very light read. It's an entertaining read. It's pretty short, optional reading. Okay, let's have a look at chapter 1 and Vehicle 1. We have about as simple a robot as you can imagine. We have a robot made up of one object, one link. It's got one wheel. That wheel is attached to the link with a rotational joint that allows the wheel to spin. We have one sensor that's attached. We have one sensor that detects, in this case, temperature. And that sensor is attached to the joint that connects the wheel to the body with one wire. Yeah? One sensor, one synapse, one joint, one body part. It's about as simple as you can possibly get. Breitenberg said, imagine what would happen now if you took that vehicle and you dropped it into a pond. It's restless, you would say, because it doesn't seem to like warm water. So imagine we have this temperature sensor here. The temperature is detecting cold water, meaning the sensor is firing at a low frequency, or it's outputting a low number. That low signal is being sent to the wheel, which causes the wheel to spin at a low velocity. As this thing is moving along, if it moves into a patch of warmer water, the temperature sensor starts to fire more strongly, and it sends that signal to the wheel, which starts to turn faster, and this vehicle will move fast through warm spots and slow down in cold spots. So far, so good? Why a pond? Because if you take a bunch of pond water and put it under a microscope, you can see things swimming around in there that act basically like this. Yeah? Okay. However, if you did see Vehicle 1, you might say it's quite stupid since it's not able to turn back to the nice cold spot that it had just passed through in its restlessness. You'd probably be drawn to the conclusion that it's alive since you've never seen a particle of matter act like this before. This is a very serious neurophysiologist. He's talking about Vehicle 1 being stupid, being restless, being alive. He knows it's not restless. He knows it's not stupid. He knows it's not alive. He knows we know. Why would he be using this kind of language?
Because of the same reason as like the Turing test, where it like fools people.
Fools people, right? You get restless sometimes, right? When you get restless, it's different from this thing. I'm restless in a special way. This thing looks like it's restless. It acts like it's restless, but it's not actually restless. Let's have a look at vehicle 2. We actually saw a Lego version of this last week. Slightly more complicated. We have one body. We now have 2 sensors, and we're going to change the modality of the sensors, meaning what particular type of physical phenomenon does the sensor detect. Vehicle 1, temperature. Vehicle 2, it's detecting light intensity. So if more light falls on the sensor fires more strongly. If less light falls on the sensor fires less strongly. Yeah? We have 2 sensors, we've got 2 wheels, and we have 2 synapses. No neurons whatsoever. This is a pretty simple brain. The brain is made up of just 2 wires. These wires connect the 2 sensors to the 2 motors contralaterally. Contra meaning across, laterally meaning side. It's just a fancy way of saying that these are crossed connections. Left sensor is attached to the right wheel. Right sensor is attached to the left wheel. All of the visual information arriving at your left eye is being processed in the back right part of your brain. All the visual information falling on your right eye is actually being processed contralaterally in the back left part of your brain. Yeah? So a little bit of neurophysiology terminology here for you. Okay, so we have this robot. Imagine we have a flashlight and we come at this robot from the front left. What does this robot do? Or what's happening from the point of view of the robot? Let's put ourselves in the shoes or the wheels of the robot. The light source is front and to the left of the robot. It's going to turn towards the light because why? Absolutely, right? So a pretty simple sense, think, act cycle here. Sense, more light is falling on the left sensor. Think, not much thinking here, but there is a stronger signal traveling along this wire than there is along this wire. Act, that means that this stronger signal causes the right wheel to spin faster, which means it turns forward and a little bit towards the light source. Let's run a mental model in our heads like we're doing this in a physics engine. We take a little bit of time. We look a little bit of time into the future. The robot has turned a little bit towards the light. What does the robot do at the next time step?
Will it go towards the light because the light will be an even distance from both sensors, so both wheels will turn?
Okay, so if we assume that it's turned enough that it's now facing the light directly, then yes, now it's going to stop turning and it's going to head directly towards the light, because at that point, equal amounts of light are falling on both sensors, which mean both wheels turn at the same speed. So it moves a short distance directly towards the light source. What happens at the next time step? It's a little bit closer to the light and facing it directly. It speeds up, right? It's a little bit closer, meaning there's more light falling on both sensors, so it moves a little bit faster. If this is a naked light bulb, it'll crash into the bulb and destroy it. This is the aggressor. It hates lights with a passion. Yeah? If we put a light on the other side, it'll turn towards that light, speed up, and destroy it. That was actually vehicle 2A, the aggressor. This is vehicle 2B. It's a twist, literally, on vehicle 2A. Everything's the same, but we're going to take the contralateral connections and uncross them, which gives us an ipsilateral set of connections, same-sided connections. Values arriving at the left light sensor are sent to the left wheel, Same thing with the right side. If we approach this robot with a light from its ahead and to its right, what does this robot do? It turns away, right? At this moment in time, more light falling on the right sensor means the right wheel spins faster, and it turns a little bit away. Let's add a little detail. Let's imagine that these two light sensors are omnidirectional. So if it's turned away from the light, it can still see the light behind it. So this robot is turned a little bit away from the light. What does this robot do at the next time step? I told you last time that programming robots is very non-intuitive. This one is so simple that for most of us it's intuitive and you can kind of figure out what it's going to do. It's turned away from the light a little bit, but it can still see the light. What does it do at the next time step?
It's going to turn away more.
It's going to turn away more. Okay, now what happens?
It's gonna run away, right?
It's going to run away, right? It's going to start to move away, basically in the opposite direction of the light. As it does, as it's running away, what happens? There's one more twist here.
Gets faster and just keeps going.
Does it get faster? Gets slower, right? As it moves away, the amount of light falling on both sensors decreases, which means the wheels slow down. So the robot is now ahead of me. I've got the flashlight. It's ran away from me, but it's slowed down. I come after it. What does it do? It speeds up again. This is the coward, right? It's afraid of light with a passion.
If you set it up such that it was initially pointing straight at the light, would it act like the aggressor though?
So what would happen? Imagine we managed to put this robot so it was facing the light source directly. What would happen under those initial conditions? It's a good question. This is a little trickier. It would speed up because there's more light, but think very carefully here. It would start to approach the light, but then something would happen. Would it continue to speed up and crush the light like the aggressor? Seems like it.
They were completely like 90-degree normal, and there was the distance between the light source and the sensors was always equidistant.
Okay, as long as everything was exactly right? The lights have to be perfectly equidistant from the light, right? Everything has to be exactly right. If we built this robot in reality, what's the chance that that's going to happen? 0. I told you last week, the Greek philosopher Heraclitus said, man never enters the same river twice. We live in the real world. Now, you're going to be building robots in a platonic world, a virtual world where things can be perfect. It's never true, right? So in the real world, that would never happen. There'd be a slight difference that would cause it to turn to the left or the right, and then it would run away as usual. Yeah. Another thing that distinguishes robots from AI is as long as an AI is trapped inside a computer and we're feeding it information, it can, in theory, live in a perfect world. No robot, no drone, no autonomous car, no 3D printed prosthetic arm or limb is ever going to enjoy that perfection, right? It's not necessarily a problem. It can be something to be exploited, and we'll see that in the next lecture when we talk about embodied cognition. Okay. If you read these chapters in vehicles, Breitenberg talks about how much this 2A hates the light and how much vehicle 2B is afraid of the light. Hatred and fear, 2 types of emotion. Last week I asked you what distinguishes us from mere machines. Somebody said emotion. Breitenberg says, my vehicles have it too, obviously. You all okay with that?
No.
No? Why not? You sometimes hate, you sometimes fear, but it's different. Different how? Think hard. You're about to get lumped in with a machine that has 2 wires inside.
We have more than 2 wires inside.
Sorry?
We have more than 2 wires.
We have more than 2 wires. We actually have 10 to the 14 wires, more or less, inside. If that's the only difference that you're gonna base human nature on, you're in trouble. Because of course, since the 1980s, we've now figured out how to build machines with many, many more wires, depending on how you define wires. We're not quite at 10 to the 14 yet, but we're getting darn close. Human distinctiveness is on the line here. Think hard. Yes?
I mean, I guess it's like robots will always act like super rationally. Like every time they'll see a light, it'll just run away. It'll have the same result every time. Versus, I might be scared of doors. I'm not scared of doors, but if I was,
Yep.
if that door scared me,
Exactly.
it changes.
Great point, right? Humans are wonderful because they're surprising, right? They don't necessarily always do the same thing twice. Okay, maybe we'll rely on that to claim that we are better than the machines. You can probably see where I'm going with this. Unfortunately, there's a problem with that defense also. What is it?
You could build randomness into a robot?
Build randomness into the robot, absolutely. It's not that hard to make a machine that doesn't always do the same thing twice. We can put a little set of dice inside and the robot can roll the dice and do different things. Some of the times, rarely, most of the time, no problem. Okay, what do we have left?
Could it be something to do with like metacognition and like the robot is behaving a certain way, but it isn't thinking about how it is behaving that way?
Great question. We are able to think about thinking, which is known as metacognition. Actually, it's what we're doing right now. We're thinking about thinking, yeah? I made my career by making a robot that metacognizes, that thinks about its own thinking. We'll talk about that robot next month, I think. So unfortunately, that one's out too. We don't have time to go through all the other possible defenses. It gets a little worrying for a lot of people. One of the things that robotics and AI and science does in general is tends to challenge our assumption we're special, we're at the center of the universe, either literally or metaphorically. I am not trying to convince you that you are a Breitenberg vehicle or a Chinese room, just setting the stage for you to think about it. What makes us special? For some of us that are spiritual or religious, it's easy. We have a soul, we have a mind, and that's the end of it. Perfectly fine. It's not a scientific argument. If you want to try and argue scientifically that human nature or higher animals think differently than the vehicles, much, much more difficult to do. Maybe not impossible, but it hasn't been done yet. Okay, let's keep going. A lot happened in the 1980s. Same time, there were a bunch of crazy scientists saying, hey, wait a second. Instead of making these big if-then-else statements like we saw before, why don't we actually try and simulate the brain? So not too differently from what Breitenberg was doing. Let's create a computer program, and inside that computer program, there'll be a whole bunch of nodes that represent biological neurons, and we'll program in a whole bunch of connections that connect these nodes together. We'll then supply some input to some of these nodes, and we'll see what numbers arrive at the output, and we'll interpret those numbers at the output as an answer to whatever we supplied as a question at the input. If the numbers are wrong, we'll go inside this thing and tune the strength of these connections until it gives us the answer that we want. And we'll repeat that process over and over and over again until we can give it some new question, encoded as a set of inputs, and it'll give us, quote unquote, the right answer. Question?
Yeah, just briefly going back.
Sure.
You said that inside of us there's how many connections? Or I was just gonna ask
10 to the 14 synapses.
like, where did that come from? Or like, what's the synapse?
So if you feel that we are different from the Breitenberg vehicles because we have more wires, yes, that is a difference. We have more wires. But we're closing in on being able to make robots that have 10 to the 14 connections inside. So if you want to rely on the fact that we have bigger brains as a defense for why we are different from machines, that difference is not going to be a difference for much longer. Yeah? Okay. Okay. This was the idea. The people that came up with this idea were laughed off the stage. This was seen as a ridiculous idea. This will never, ever work. In the 1980s, they could create these things that they called artificial neural networks. They could get them to solve simple problems, but they couldn't get them to solve harder problems. Most people gave up and moved away from the field. You were actually told, if you were a new academic in the late 80s, 90s, into the 2000s, never use the word neural network. The rest of your peers will think you're a crackpot. So it's a dead idea. Forget about neural networks. It'll never work. Thankfully for us, there were a few researchers who persevered. They worked out some of the math to get all this stuff to work, and they were quite smart. They rebranded the field. Instead of talking about neural networks, they started to talk about deep networks. They reported this sort of mathematical advance in about 2006. That was the atom bomb that went off. That was the beginning of the AI revolution. And as we all know now, where are we since 2006? So 15, 16 years on, they clearly work, and they work really, really, really well. Which means today we are enjoying what's known as an AI summer. The history of AI, which started with Alan Turing in the Second World War, has gone through boom and bust. There have been periods where people sort of lost hope and said, we're never going to make intelligent machines, or at least it's going to take us 1,000 years to make intelligent machines. It's super hard, maybe impossible, let's give up. That was an AI winter. There were several of them, one in the 70s, another one in the 90s. We are now in high summer, right? Everyone on the planet, regardless of how technically inclined you are, knows that something is happening in AI. AI is getting better in some way. Maybe deep learning will run out of steam. Maybe ChatGPT or whatever comes after it, ChatGPT, whatever comes after it, maybe that's it. Maybe after that we'll see some diminishing returns. Maybe we'll start to enter back into an AI winter. Or not. Or maybe the summer will continue, we'll just keep making smarter and smarter machines. Who knows? Again, this is a lecture on the history of AI. One of the fun things about it is it's a roller coaster. There's been periods of boom and bust. An early roboticist from the 1980s, Hans Moravec, he published a paper trying to explain these AI winters. One of the reasons is if you're a researcher, you need to ask the government for money. And of course, you're not going to tell the government, this probably won't work. AI is really hard, maybe impossible, but give me some money anyways, and let's see if we can make it happen. Of course not. You promise, if you give me some money to do this, we're going to figure out how to do X, Y, and Z. You get the money. If you go back to the government, you can't say you're going to do the same thing. You've got to promise more. So you get onto this hamster wheel, or the academic community gets onto this hamster wheel where they promise the government more and more beyond what they can do, until eventually the government calls the academy's bluff, all the funding shuts off, you dive back into another winter. We are not in a winter at the moment. Most AI researchers can sneeze onto a piece of paper, give it to the government, and they'll get a pretty good grant back from it. Doesn't take a lot of effort at the moment. Okay, as you now know, this is the current era we live in. This is not a class on deep learning, but it's worth touching on this for a moment. We've now seen neurons connected by synapses to other neurons. What was this conceptual advance that was made back in 2006? It was to figure out how to make more layers between the input and the output. In this cartoon example here, we've got two outputs. Imagine the two numbers arriving at these outputs. If the first number is bigger than the second number, that's the neural network trying to tell us, I think there's a cat in this image. If the second number is larger than the first number, we're going to interpret that as the neural network trying to tell us, there's a dog in this image. Cat, cat, dog, cat, dog, cat, dog, so on, right? What do we do at the input layer? We show it a whole bunch of photos of either cats and dogs. If you wire up this whole monster at random, as you would expect, it's wrong half the time. It doesn't know anything about cats and dogs. The conceptual advance was how to tune the strength of all of these connections, so that after a while, after presenting millions of images of cats and dogs, this thing actually gets really, really good at detecting cats and dogs, or whatever it is you want it to detect. If you then break open this neural network and look inside after training, after it's learned to distinguish between cats and dogs, you see some interesting things. If you take a neuron like this, which is close to the output node, and you set it to a maximum value, and then you push the values in the opposite direction. You go from this back upstream towards the input, and you interpret all the values arriving at the inputs here as pixel values, you often get something that looks like this. Somewhere else, if you stimulate it over here, in this case, it's recognizing obviously humans, and push the values back down, it'll tell you that this neuron is about humans. This neuron is about cats. If you do the same trick with neurons that are closer to the input layer, you get things that don't recognize human faces or cat faces. It's things that recognize parts of faces, diagonal lines, little circles, vertical lines, and so on. The conceptual advance was training this neural network to basically learn features, and then how to combine features and combine features and combine features into pictures of cats and humans and everything else. Interesting in and of its own right, even more interesting because it looks like a lot of your brain is organized in the same way. If I were to put a probe into your brain at various places between your eye and the back of the brain, which is where you process images from your eyes, you would see something very similar. Neurons close to your eye are sensitive to local features, short diagonals, short verticals, short horizontals. Neurons that are further downstream, further towards the brain, when you stimulate them, they're recognizing whole faces, your grandmother, your aunt, higher level features. Yeah? Okay. Okay. However, as we all know, it's not perfect. You can take the state of the art, or as of a couple years ago, give it a picture of an apple, and you get what you'd expect. It'll tell you that it's looking at not just an apple, but a Granny Smith apple. You can then slap a sign on the apple, and it will switch and tell you it's absolutely sure that it's now looking at an iPod. Yeah? Adversarial attacks are well, they used to be the skeleton in the closet. The skeleton's not in the closet anymore, right? Everybody knows. It's actually not that difficult to trick state-of-the-art AI, including ChatGPT. Here's another example, a historical example. Here's Eliza, the very first chatbot. A couple of years ago, I found a version of it online, and here I am talking to it. So here it is saying, I'm Eliza. I answer, I'm Josh. How long have you been Josh? I say, my whole life. It says, tell me more. I ask it a question. How many eyes does a giraffe have? Eliza's pretty smart, right? She kind of changes the subject. Same thing with with GPT-3. How many eyes does a giraffe have? Not only does it not sidestep the question, it gives me the right answer. However, we keep going, you can start to see the cracks underneath, right? Not unlike this. What's going on? AI has gotten incredibly powerful, but all of these AIs seem to have these Achilles heels. Why? What are they missing?
Magic sauce?
Maybe the magic sauce. That's one answer. That's one possible answer. Maybe they're missing the magic sauce. A little bit less magical. They kind of seem to be missing like common sense, right? Like a little kid, would be able to pass this test, presumably, right? Or at least maybe wouldn't have super confidence that they're looking at an iPod. So superficially, a lot of folks in the community say, they're kind of missing common sense. They don't really understand cause and effect. This machine doesn't know that there's a human somewhere who's trying to trick it, right? There's stuff going on here beyond just the apple and the sign, right? There's a prankster somewhere off stage that most humans can figure out pretty quickly, right? So they're very smart, but they somehow lack common sense. They don't kind of understand cause and effect very well. Yeah? Why not? Why are AIs so smart, but lacking in common sense? This is one place where humans seem to still be doing a better job. Most of us have maybe not great common sense, but more than this.
I think part of it might be that the training data that we're giving them don't have a lot of prank entries in it.
Some folks in AI would say just give them more images of pranksters trying to fool them, and that'll patch over this iPod Apple problem. Good, problem fixed. Putting a Band-Aid on a crack in the dam, right? It's not just this example. There's probably gazillions you could come up with. But you're on the right track. Yeah?
I think part of it is like with the iPod thing, the thing you're training is just image recognition. Like it's just looking at the features of an image and like making like a really simple like comparison to other images, but it's not taking into context like what a like the meaning of like a sign and like what the intention is of a person who would put a sign. Like it's not thinking beyond just like what you told it to like that.
It's not thinking beyond, you're right, the training set of images. Of course it's not, because it can't. It's imprisoned in a computer, and all we've done is held it down and given it a whole bunch of images and the answer. This is a Granny Smith, this is an iPod, and so on, right? Look, thank goodness for us, that is not how we train our kids, right? A kid could probably pass this pretty quickly because most young kids have spent time on a playground or in kindergarten, and they already have thousands of exemplars of someone playing a trick on them, they playing a trick on somebody else, watching someone play a trick on someone else. There's another trick. That was actually not a trick, that was just a mistake. They have experience from the real world. Our children can push against the world and observe how the world pushes back. They have a body with which to explore the world, get pushed upon, again, literally and figuratively. Our children, with their bodies, and every organism that's ever existed on this planet for the last 3.5 billion years, has a very different training set. Yeah? Physical experience over which the organism has partial agency. I can influence to some degree what happens to me. I can understand cause and effect better than GPT-3 because I can cause effects. I can observe the sensory repercussions of my actions. That is the thing that distinguishes robotics from AI. As I mentioned, there's a lot of, as you've seen in the history of AI and still today, there are many different camps. A lot of folks in AI just say, nope, we just need more images. We need more images of people playing tricks on AI. We'll solve the problem. We don't need to put this thing inside a body and have it gain experience in the real world. Roboticists say there aren't enough images in the universe to develop a sense of common sense. You're going to have to create intelligent machines by giving them bodies and allowing them to interact with the real world. Nobody knows yet which of these two camps is right. Maybe both of them are wrong. Maybe it's something else. But obviously in this class, putting my cards on the table, I belong to the latter camp. If you want a machine that is smart and has common sense, it's got to be able to cause effects in the world and learn about those effects. Yeah. You don't have to agree with me. You can come to your own conclusions in this course. Just putting my cards on the table. Okay, so as promised, as you can see, the fields of AI and robotics are bicameral. They have two branches. We're going to spend most of our time on this side of the camp. This was probably the only lecture where we're going to spend most of our time talking about this side. Lots of different kinds of robotics. We're going to talk about evolving robots. Someone made a point earlier about human children developing. There is another field of robotics that treats robots as babies and tries to get robots to develop into commonsensical actors in the world using ideas from developmental psychology, the study of children. Also a valid approach. Other roboticists think it doesn't matter how smart you are or commonsensical you are as an individual, you need to be social. You need to be a part of a group in order to develop intelligence, and common sense. Those are the swarm roboticists. Other roboticists try and build robot dogs and snakes and birds and so on. They're taking direct inspiration from nature. Industrial robotics, that's a solved problem. We're not going to talk much about that in this course. So we're going to spend most of our time here. We'll dip a little bit into some of these other branches throughout the rest of this course. The line between these is this Cartesian dualism that we talked about at the beginning of this lecture. Everything on the upper right side of the line is referred to as embodied intelligence. Everything here has a body. Everything down here on the lower left doesn't. Which of these two teams is going to produce a machine that really passes the Turing test? We'll see. Who knows? Okay, we've got 4 minutes left, so we will start in on lecture 3, which addresses exactly this question. What is this idea? What exactly do I mean by this idea of embodied intelligence or embodied cognition? We're going to explore this idea of embodied cognition in this lecture series by looking at a bunch of building blocks of intelligence. And we're going to look at non-embodied approaches to that building block and embodied approaches to that building block. As Turing told us, it's very hard to define intelligence. It's slightly easier to point to a bunch of different behaviors and label them as sort of the building blocks of intelligence. If you're not capable of this behavior, you're probably never going to be intelligent. What is one of those building blocks? There are many. One of them is pattern recognition. If I can't tell the difference between friend and foe in the world around me, or the difference between food and poison, I'm not going to be around long enough to evolve the ability to be intelligent. Yeah? Okay. Researchers all the way back in the 1940s and 50s realized this was important, so a bunch of them who eventually became known as computer vision folks tried to give computers vision. They attached cameras to computers and allowed the computer to look at the world, and the computer was supposed to be able to recognize patterns in what it saw. Yeah? Turns out the researchers learned very quickly this is super, super hard, right? Hopefully most of you recognized who this was almost instantaneously, right? It feels effortless. Turns out it's not so easy to do. A slightly easier problem, rather than just recognizing who this is known as the image segmentation problem. Just separate foreground from background. Here you can see the computer attempting to do that. Not a very easy thing to do. We can do it today with GPUs and 1 billion photographs that either do or do not contain Marilyn Monroe. Very, very hard to do. Yeah? That's the non-embodied approach. Create a deep neural network, give it a gazillion images, and let it train on those images for a long time. Here's the embodied approach to the exact same problem. We were not going to be able to get through the entire description here, so we'll just start. This is COG. If you make it to the Science Museum in Boston, COG is now retired. You can find COG in the museum. Back in the early 2000s, some researchers did an experiment by trying to teach COG to recognize objects or patterns in its environment. How does COG do this? Well, as you can see in the cartoon here, COG has 2 eyes. These are 2 cameras. And it has 1 arm and 1 hand. So at every time step, this physical robot COG is receiving pairs of images from the cameras. The researchers wrote some code that took those 2 images, combined them, and scrubbed out a whole bunch of information. They threw away all the color information. They threw away a bunch of other things. They basically left the pixel as either black or white, which is represented here as shaded out or not shaded out. So basically, the robot is getting a binary image. Shaded out means at that particular pixel, there was no movement over the last 1/10 of a second. Non-shaded out pixels represents there was movement at that place over the last 1/10 of a second. So kind of a strange way to start. They're kind of partially blinding the robot so that the robot can only see motion and lack of motion in its environment. Seems like an odd place to start. We'll pick this up again next Tuesday and see how Cog is able to recognize patterns in its environment. You have a quiz due tonight. Undergrads, you're working on assignment 2. Grads 3 and 4. Have a good rest of your day.